Good afternoon, everybody. My name is Craig Piercy, and I'm the CEO of the American Nuclear Society. And it's my pleasure to welcome you to today's discussion focused on the people and organizations working toward achieving nuclear reactor criticality, some by July 4th of this year. Today's program is made possible by the ANS Trustees of Nuclear, our premier corporate membership program, which supports improved K-12 nuclear education opportunities and more technically informed conversations about nuclear with policymakers, journalists, and the public. To learn more, visit ans.org/trustees. So before we jump into the conversation, let me briefly frame why I think it matters. So for the first time in decades, the US is not just talking about new nuclear, we are actively building toward it. And what makes this moment especially interesting is we're seeing more than one pathway to deployment playing out in parallel. Some teams are working toward near-term criticality, potentially or as early as July 4th of this year, under DOE authorization frameworks, which enable faster iteration and demonstration. At the same time, others are advancing through the NRC licensing process, which may be more deliberate, but ultimately defines the pathway for broad commercial deployment at scale, and yet still does allow for iteration, as we'll hear today. These are not competing approaches, they're complementary strategies, and together they represent kind of a dual track model for rebuilding nuclear capability in the United States. And all the while, national laboratories are playing a key enabling role, providing expertise, infrastructure, and a proving ground to move advanced reactors toward demonstration. Today's panel reflects that full spectrum, teams working together under different constraints, timelines, and definitions of success, but all pushing toward the same end state: repeatable, reliable, deployable new nuclear energy. So without further delay, let's welcome today's guests and get into it. Yasir Arafat is the Chief Technology Officer at Aalo Atomics. Jordan Bramble is the CEO and co-founder at Antares. Nader Satvat is Director of Nuclear Systems Design at Kairos Power. Nick Thompson is an engineer at Los Alamos National Laboratory. And Brad Tomer, the director at the Idaho National Laboratory's National Reactor Innovation Center. And last but not least, Rita Baranwal, Chief Nuclear Officer, Radiant. So we've got a fully packed panel today. Everybody pop their cameras on. And let's jump into opening remarks. And Yasir, I'm going to start with you. Tell us a little bit about yourself and tell us a little bit about Aalo Atomics.
Awesome, Craig. Thank you so much for having me on today. Just a quick background about myself. It's a story about how I got into nuclear in the first place. Grew up in Bangladesh, and growing up, there were two main things that I've seen that kind of shaped my career. One was climate change. It's a very low-lying country, so anytime there's a water level rise, it would wash away a significant portion of the land. So that was very impactful to me growing up. Unlike the West, where we argue about climate change, we kind of lived through it growing up. The second issue was electricity shortage, and every day we would have daily brownouts. So that ended up studying in candlelight most of my young life. So that also was something I was passionate about to work on. When I came to the States and started college in engineering school, I ended up learning about nuclear, and I was like, wow, this technology can solve both of those curiosities. And that was the beginning of my path essentially I started working at Westinghouse, and a lot of familiar faces here on the panel. But since then, I've worked on 5 different reactor projects. I was fortunate to be able to work from gigawatt scale all the way to kilowatt scale, and I'm excited to talk about what we are doing today at Aalo Atomics. So, all those lessons learned from the various programs we have plugged into, Aalo, which is a relatively newer company. And what we're trying to do is, trying to make mass manufactured nuclear reactors a reality. So even 6 months after we started Aalo, we didn't wait for design to be completed. We said, let's go ahead and actually build the muscle to build real hardware so we can learn from design for manufacture, build the assembly along with the design process. And that is just the first step, right? We can only make one reactor at a time in this facility. It's only 40,000 square feet. For us to really scale at the level we're talking about, we need something called a gigawatt factory. This is our goal of deploying 1 million square feet, which will spit out 100 reactors a year. By 2028, our plan is to deploy a larger factory leaning on the learning from the pilot side. And with that, I want to say a kind of a bold statement is like by 2030, what our company is working towards is to deploy at least 1 gigawatt by 2030. That means 100 reactors that we're basically designing, rinse and repeat. Now we know that, every nuclear reactor, we can't just like pretend we can vertically integrate everything. You actually need a village to bring a reactor to life. So we've been working with a host of companies, suppliers, partners, trying to make sure that we can make this reactor a reality. So far, we've been working with 127 suppliers across 35 states and 6 countries. So we're bringing a lot of that muscle to make sure that we can execute on this goal. Okay, with that said, quick overview. We've been going pretty fast. We're only a 2.5 year company, literally from 2 person to about 150 employees in about 2.5 years. We've done quite a bit. We've got 2 facilities, one in Austin, the other one in Idaho Falls. But ultimately, we got selected for the DOE Reactor Pilot Program, which we're very fortunate about. And I'm going to show a little bit of what the latest and greatest is on that very program. This is what is called the Critical Test Reactor. This is a facility that we have designed and built from ground up, starting from the building all the way to the reactor, to the fuel, the whole 9 yards. So again, the reason why we embarked on this is not just to collect physics data that can help us, tackle the full power reactor, but also to understand like what are organizationally, are we ready to execute on a real program, including all the safety management programs, construction, supply chain, exercising everything along the overall, the value stack. We're 95 days away, and I'll give you a quick overview of what we have done so far. We have had some criticism saying, hey, you can't even build a tool shed at the lab under 2 years. Forget about building a reactor building. So we ended up building our entire building in like 36 days, which was kind of unheard of in modern times. Because of our factory, we ended up building our entire reactor in a matter of 4 weeks from start to finish. And then lastly, when we brought in the reactor into the empty building, this is what it looked like on day 1. And that's day 7, where we installed the entire reactor with the X-core shielding, all the CRDMs. The only thing that's missing here is the core and all the wiring that we're working on right now. So bottom line, we've been trying to move pretty fast without sacrificing quality and safety. And that's a very important aspect that we didn't want to give up for speed. We also have our fuel completely made by GE, and they're packaged, ready to ship. In fact, today is the day when GE is going to ship that fuel over to INL, and we're going to be ready to load the fuel as soon as we get the full approval from DOE. So bottom line on the overall chart, all the green stuff are things that we have accomplished. We still have a few things left on the roadmap to finish. We're waiting on the final DSA approval from DOE, readiness approval, and then we'll put the fuel in and go critical. Again, we're talking about 7-8 months from start of a project all the way from, splitting atoms. So, and a lot of my peers on this panel are working towards very similar timelines. So that's been a very rewarding experience for us. But that's just a starting point for us. It is not the end goal. The end goal here is to build a full powered reactor, which we're planning by the end of this year. This is a sodium thermal reactor that is fueled by 8% UO2. And we don't have time to dive into the details, but it is, all the way from heat generation to electricity generation. We want to demonstrate the whole 9 yards. And learning from here will ultimately go into a full pod. All of these tests that I just covered so far will be done in a single piece of land right outside of the MFC complex at Idaho National Laboratory. Anyways, sodium-cooled reactor technology is very mature, but we are not the ones that build those reactors in the past. So this is our technology readiness roadmap, where we're iteratively learning from one hardware to another. So starting from TRL6 on the left-hand side, where we build a sodium test loop to test all the components that will be wetted in sodium, to the critical test reactor that is pretty much done. We're waiting on the last final steps there. And then learning from there, we'll go into our full-scale non-nuclear prototype Aalo Zero, and then we will combine those learnings to get the Aalo X, our full-scale first power reactor that we're building also at INL. And then all of these learnings will feed into our commercial product, which is basically 5 reactors connected to a single turbine, which we think is the ideal product market fit for data centers. So I know a lot of information in 5 minutes, but let me pause here and excited to dive into the question Q&A session for the panel.
Yeah, thanks, Yasir. Appreciate that. So now I want to turn to Jordan Bramble, CEO and co-founder of Antares. Jordan, tell us about you and your company.
Hey, everybody. Thanks for having me. Really excited to be here. Um, really quickly, I mean, my journey into nuclear. So, engineer by background, studied systems engineering and physics. My first kind of real world job was at the Newport News shipyard on naval submarine construction, and spent a great portion of my career in startups. I've worked, in artificial intelligence, machine learning, embedded systems, done a lot of multidisciplinary engineering leadership. But I was also in OMB in the White House, and so have kind of a little bit of a policy background as well. And I think what we found at Antares is really bridging those two areas is a huge part of getting these things built. Turns out advanced reactors get built in Washington D.C. just as much as they do in Idaho, right? But for me, what I love about nuclear energy and what I find so rewarding about working on it is, you know, clean energy is incredibly inspiring to work on. Space exploration is incredibly inspiring to work on. So is national security. Nuclear energy is just kind of this beautiful technology, this amazing form of energy that allows you to work on all three, right? All three of these really big, important problems. We all know this nuclear energy is really the only clean and firm energy source that we have. In the past, the negative is it's just not been affordable or fast, right? And that's really where we come in this new crop of companies is figuring out how to kind of finally be all four of these. At Antares, I mean, our focus is fission powered systems for defense and space applications. We want to eventually do commercial as well. In fact, we are starting to expand into commercial opportunities, but we really believe the DoW and kind of the federal government largely is going to be the best first customer for these technologies, not unlike semiconductors, GPS, rocket propulsion, many such examples throughout the last century or so. And kind of what we noticed is there was really this lack of industrial partner that was like truly focused around doing this. You have microreactor developers that have a lot of the technology expertise, but much less so on the mission architecture and concept of operations for these customers. You kind of have large prime contractors that have that expertise but miss some of the nuclear expertise. And so we really thought there was this opportunity to build this new industrial partner for the DoW. The other thing that we kind of believe is foundational for us is the market winners for microreactors and for space nuclear. I think that'll be decided kind of within 2 to 3 years of each other. And I think that looks increasingly true now that we're seeing NASA's announcements on the SR-1 Freedom mission. And it's really important to us that we have a role to play in both. And so we architected the company from the very beginning around doing both. It's one of the reasons why we're a heat pipe cooled system. The way we think about it is like the scale of terrestrial deployment will enable cost improvements for space nuclear power and propulsion. And space is where we're going to push our advanced materials or advanced fuels that will ultimately be able to incorporate back into more performant terrestrial products as well. Us as a company, so we've raised over 140 million of private capital. We have over 322,000 square feet of manufacturing space that's live and operational today. We plan to build our first 30 to 40 reactors here in Torrance, California. We have smaller satellite sites in South Carolina as well as Idaho Falls, just outside of Idaho National Lab, where we're building this first reactor that'll go critical before July 4th. And on the customer side, we work with every service in the military as well as NASA. In terms of criticality by July, when the president's executive orders came out, we really saw that as a call to action. And I remember being at out in Idaho Falls, and we rented a conference room at the Residence Inn there, by the bridge. For those of you that have spent a lot of time in Idaho, and we just kind of had this sort of brainstorming session as a company, and we really realized we were in position to go do this. We already had a facility at INL that we were investing our own money into to get it to an operational state. We had a pathway to fueling the reactor. We had already been working with DOE on a DOE authorization pathway, and so we really felt like it was an opportunity to move fast. But what we really wanted to do was make sure that what we were going to do by July is integrated into a broader technology maturation strategy that ultimately results in a commercial product. And so, kind of our North Star is getting to an electricity producing prototype reactor that can be a long-lived test. This first criticality that we do is really a stepping stone to that. So, when we think about the value that we're getting out of this first criticality test, it is a huge validation of the performance of our control systems as well as our reactor physics. But more broadly, no one has ever licensed an advanced reactor under DOE 1271, let alone DOE 1189. This is kind of like the MVP, the minimum viable product pathway through that regulatory process. And so, we are becoming a much more capable and competent institution as a part of this. It's a huge kind of debugging and shakedown of our underlying supply chain. Like, it's this moment where the rubber meets the road and you see what's working. It's been a great guide for us to develop our fueling ConOps, like how the reactor ultimately gets fueled, our assembly techniques, and we're gonna essentially very, very low activation in the facility. We're going to be able to turn around and start working in there again pretty quickly after July. And we're going to scale up to eventually power operations and producing electricity outside of the building. So, thank you again for having me.
Excellent. Thank you.
I think I kept it to 5 minutes.
I think you were pretty close. I think you got it just under the gun. Nader, let's turn to you, Kairos, and maybe a little bit about your journey and about where Kairos is. Obviously, NRC focused. Looking forward to your presentation. Take it away.
Really grateful to be on this panel with this distinguished group of people who are doing the deal in a very exciting time. Thanks, Craig, Dan, and Brett for the invite, and also hello to all the participants. My name is Nader Satvat. I'm the Director of Nuclear Systems Design at Kairos. We always start with our mission, which is to enable the world's transition to clean energy while improving people's quality of life and protecting the environment. And to achieve this mission, we are focused on delivering a technology that is safe and affordable. Essentially, the entirety of philosophy of how Kairos was founded is around affordability, being able to deliver a technology that is meaningfully part of the solution for energy transition to clean energy. A quick journey to nuclear. I was fascinated by physics from very early on as a child. I always wanted to understand the secrets of the universe. Then I realized it is not just that I want to understand it, I also want to have impact. I was very fascinated by all the pioneers of 20th century physicists. And so I picked engineering as a natural choice. And I picked nuclear because it was closest to physics. So I wanted to get both of the best of the both worlds. And I went to Purdue as an undergrad all the way through grad school. And I am very grateful for professors at Purdue. I consider them my mentors, and their mentorship brought the mental clarity that nuclear is not just a luxury choice, it actually is a necessity. And I pursued with a very clear purpose from that point on. And I want to shout out to a mentorship program in American Nuclear Society. If you are a high school student, you're starting out early on your journey to nuclear, pick a mentor. And the way I describe a mentor is someone who they have something you want and you look up to, and follow their guidance. You will win big. You will gain a lot of headwind in your journey. With that, I'll go into Kairos Power's path to commercialization. I talked about affordability. Nuclear is behind because of that, because it takes long, because it's always been very expensive. The conventional nuclear development is a model that needed to change. Kairos Power started basically with a vision of building an organization that is committed to building. From day one, when I came for an interview to Kairos, I remember there were like 20, 30 folks at Kairos at the time. And every desk on the small office in Oakland had a bunch of different hardwares and small tests on them. So from very early on, it was committed to build and sequence of large integrated hardware is the key to understanding where these systems are going to fail, because this technology is intended to produce energy and be financially viable. So they need to run reliably. Reactor physics is not what fails the project. We all know it's a pump not operating the way it's supposed to operate, not access for maintenance, or a valve not playing game where they need to play. So these integrated hardwares has been teaching Kairos a lot. The four pillars of cost certainty is the cornerstone of why we're doing all these number of large hardware, integrated hardware developments. Number one is that we need to know that technology is working. Two, we need to be able to license the technology. And number three, a robust supply chain to be able to scale. If you're going to deliver nuclear to our customers at scale, the only way to do that is having a supply chain that we have exercised. It is not just on paper. You have gone through the hardship of putting an integrated system together through that supply chain. And also build process. Build process, specifically the construction aspect of it, has been one of the biggest teachers of iterative development in Kairos. And we'll touch on that a little bit on the next slide. So if you hit these four pillars, cost certainty is a natural outcome for our end customer. And that's basically what has been the philosophy of Kairos as the company. One also key important outcome of this hardware iterative development is building a robust engineering organization. The teams that are behind delivering hardware at scale, they need to have the experience. Workforce is obviously one of the open items of nuclear at scale delivery, and Kairos has been also addressing that by basically putting our workforce into delivering actually what they need to deliver as the end product. It's a quick overview here. Actually, I have a live view on a screen here. I wish I could show you all that the construction of Hermes 1 is actively happening on the left side. That's the foundation going on. We are learning a lot about scaled construction, modularized construction from Hermes 1. And when I say we are learning is always a process that brings things that we were not expecting. And a robust organization is one that can respond to those learnings and create a path for the next iteration. And Hermes 2, which I'm very happy to share with the public that the construction is going to start next month in April, which is our demonstration power reactor, is learning quite a bit from Hermes 1 construction. So that's the beauty of iterative development, which allows also parallel projects to move forward. On the right side is ETU2 vessel. It is almost identical to Hermes 1 reactor, our test reactor. All the components, all the critical components of that design has been designed, manufactured, and put together at Kairos Power. There is also, if you see those skids that are colored blue, those are actually the Lego pieces of the modularized build. ETU2 was the first opportunity for Kairos to modularize the design, decompose design into different Lego pieces, and work on interfaces from design to fabrication to also assembly engineers working concerted together to bring these Lego pieces together. And ultimately, those Lego pieces will be built for Hermes test reactor in our Southwest reactor component manufacturing, put on a truck or trucks, and be sent to that building on the left side, on the back corner. Left side of that building is actually the modularized build for Hermes 1 and Hermes 2 reactor series. Vertical integration is a big component of how we have confidence in delivering reactor at scale. Reactor component manufacturing, the system, modularized system construction, fuel, and molten salt. It also allows Kairos to go down the value chain for safety-related components in order to bring the cost down in a disruptive fashion. There is one component that's not seen here, and that is an integrated, a vertical integration on our modeling and simulation, stemmed into our own testing for validation and qualification for materials, and augmented with irradiation data from external support, in order to essentially construct the safety case of the reactor and deliver this hardware repeatable under a robust quality program at Kairos Power, which all those elements are part of our vertical integration. With that, I'll just end with this. The challenge is great, but so too is the opportunity.
Thank you, Nader. All right, we're moving next to Nick Thompson from Los Alamos National Laboratory. Nick, I know a little bit about your journey, having been a longtime ANS member, but talk a little bit about that and really how LANL is working with these vendors to support the advancement of nuclear.
Yeah. So a little bit about me. I actually started in college as an aeronautical engineer. I grew up in a town where there's a lot of aerospace activity. I really loved planes. I ended up taking an intro to nuclear engineering course taught by Dr. Peter Caracappa, and immediately decided to change majors. I ended up getting my bachelor's, master's, PhD in nuclear engineering. I did 2 summers at Knowlton Power Lab, and then came on to LANL as a postdoc and did a year over in Paris at IRIS and now ASNR. And now at NSERC, I'm a crew member, is the equivalent of a reactor operator on all 4 of our critical assemblies, and I've been doing critical experiments here for about 8 years. So with that, what is NSERC? NSERC, National Criticality Experiments Research Center. It's the only general purpose critical experiments research center kind of in the world. In the US. We have 4 critical assemblies that allow for a wide range of critical experiments from subcritical all the way to above prompt critical. We have a large variety of special nuclear materials, different shape sizes, and we've been doing these experiments either at Los Alamos or at NSERC since the Manhattan Project. Most of our work is supported by the Nuclear Criticality CD program, but we've recently been doing a lot of work that supports the nuclear energy as well. So I want to highlight the DEMOS testbed. This is a advanced reactor testbed built on the COMET critical assembly. And this was funded at LANL by the LDRD program. So you basically have this big graphite monolith and then this center monolith. And as you bring the center of the monolith up, you increase the reactivity and to get it go critical. Reflected by beryllium, and it's fueled by HALEU TRISO. This is actually a picture of one of those HALEU TRISO compacts that we have. And that center portion, we can replace it with different materials, geometries, depending upon what experiment we're trying to do. So I also want to highlight the DNCSH program. There's a long acronym, it's up there, I'm not going to read it. But basically the goal of this program is to make HALEU criticality benchmarks, specifically for transportation, storage, handling, and processing of HALEU, to help reduce uncertainties, increase mass limits, help out with NRC licensing. Call 2 results were just announced last week, and call 3 will be announced soon. We've been working closely with the DNCSH program. This is actually fuel that new HALEU TRISO fuel we're able to get through the DNCSH program, and that's going to be available for use in call 3. So if you have any ideas for experiments you like to do, critical experiments you like to do, please let us know. Some of the nuclear energy collaborations projects that I want to highlight. There's been a lot of talk about the Aalo Atomics experiment that we did. This bottom right picture is part of that, where they put their center portion of the core in. We also did an experiment with Oklo. We've done an experiment with Kairos, where that's actually down here. We took that center portion of the core, replaced it with, we put in some polyethylene, borated polyethylene, stainless steel in different configurations. We did an experiment with TerraPower. Some of you guys from ANS might recognize Matt Worgan over here on the board of ANS. With that one, we have HEU plates that are also mixed with plates of salt to measure the sodium reactivity. We're working on a project with Antares as well. We have another project with Kairos that's coming up. And then 2 projects that I just want to highlight, 2 additional projects. One's called Zeacore, and this is another LANL LDRD, so internally funded project. And the idea was to design and do the initial testing for 5%, 5 weight% fueled mech reactor, UO2, use a commercially available fuel, uses heat pipes and advanced moderators that were actually built at LANL. And we're going to be bringing this critical on the Deimos test bed this year. This also has a vacuum chamber where we'll be doing heated experiments up to about 800 C. And then also Westinghouse, one of our biggest partners that we've been we're working with them for about 4 years on. We're going to be doing a small-scale demonstration of their Vinci mech reactor using that new heliotriso fuel that I just highlighted, and do heated experiments up to the operational temperatures of their Vinci reactor. We're also going to be doing some room temperature measurements as well that will be made into public benchmarks in the Criticality Safety Benchmark Handbook. And that is also a collaboration with the DNCSH program. If you have any questions or any ideas for collaborations, please feel free to reach out. Thanks.
Thanks, Nick. All right. So next up, we're going to go to Brad Tomer, director at INL's NRIC laboratory. Brad, over to you.
Yeah, thanks, Craig. Thanks for having me today. It's great to be a part of this discussion. In terms of my journey to nuclear, I'm relatively new to the nuclear industry. I joined the National Reactor Innovation Center about 6 years ago. My broader career has actually been across the energy sector. I spent a significant amount of time in oil and gas and in large-scale energy systems. That included some time at the National Energy Technology Laboratory, where I had held multiple positions. I led oil and gas programs there for several years and resulted in a lot of commercialized products going out into the oil and gas industry. So I moved on to a multi-billion-dollar demonstration program where we built some large-scale carbon capture and utilization systems. And then I moved on to be the chief operating officer there. From there, I moved to a company called GE Oil and Gas. I was general manager for the advanced technology and systems engineering there, where I worked on commercializing technologies across the full oil and gas value chain. So during that time, I did lead the development of some technologies that we ultimately used to launch a new company under GE Ventures, which I led through a successful exit as well. That had to do with a lot of AI, or machine learning, I should say at the time, robotic inspections, et cetera, for the oil and gas industry, as well as the power industry. What drew me towards the nuclear industry wasn't really a single moment. It was more a realization over time that nuclear had to be a large part of the long-term energy equation, having been through a lot of different types of energies and working in that area. So I've been working on a lot of complex energy challenges and helping move technologies from concept to commercial deployment. And nuclear seemed to present an opportunity for me to bring that experience into a new and critically important space. So joining NRIC gave me the opportunity to take everything I'd learned and worked on before in large-scale demonstrations, complex project delivery, and startup leadership, and apply that to one of the most important challenges that we face, actually getting advanced reactors built, tested, and to criticality. So my origin story is really about coming into nuclear from the outside, recognizing the gap between innovation and deployment, and now working to help close that gap, supporting developers in the first path to criticality and beyond. In terms of NRIC, the National Reactor Innovation Center was established in 2019, so we're still a relatively new program. But our mission is very focused. We are partnering with industry to bridge that gap between the R&D and commercial deployment of advanced nuclear technologies. We are a national program. We are headquartered at Idaho National Laboratory, but we are part of the Department of Energy Office of Nuclear Energy. And everything we do is aimed at accelerating the path to nuclear energy deployment. So we have a portfolio that we get a good bit of funding from DOE for. Our portfolio really breaks into two main areas. The first is deployment infrastructure, siting, and technical support for industry. That includes both our test beds and the newly announced nuclear energy launch pad. So first on the test bed side, we design and build environments where developers can bring their reactor technologies, install them in a prepared infrastructure, and then safely take them to criticality without having to build the entire site from scratch. Our flagship example of this is the Dome facility, where we've repurposed the old experimental breeder reactor 2 containment structure into a test bed for advanced reactors. We can handle up to 20 megawatts thermal using less than 20% enriched fuels. And we're preparing for our first reactor demonstration there, which is going to be Radiant's Kairos demonstration unit. You're going to hear from Rita next on that one. So I won't say too much about that. But complementing what we're doing there in the test beds is the nuclear energy launch pad that we just announced a few weeks ago. The nuclear energy launch pad builds on the DOE's reactor fuel pilot programs and expands that into a broader, more flexible deployment pathway. It offers developers DOE authorization through 2 paths. One at the Idaho National Lab, where we have set aside 2,000 acres available for siting advanced nuclear projects, and a second we call Launchpad USA pathway that enables projects at other DOE sites, national labs, and even non-federal locations. It's important to remember that this isn't limited to reactors. It's designed to support a full range of advanced nuclear technologies, including fuel fabrication, recycling, enrichment, and other enabling infrastructure. We are going to be issuing a request for applications here in the next month for the first round of projects that go into Launchpad. So look for that to be coming out shortly. The other part of our portfolio really focuses on cost and scalability. We have a program in advanced construction technology where we're developing technologies for construction that can lead to significantly decreased cost and more schedule certainty, and reducing that certainty over time. Increasing that certainty over time. Digital engineering is another area of expertise. I once, for part of my career, served as the chief engineer for GE Oil and Gas. We did design very large things that we put out into the bottom of the ocean. We designed this very quickly, very efficiently using digital methodology. So we're trying to bring that in. We're using that for our test beds and other things, and trying to bring that to the industry as well. And we're looking at new market applications such as maritime, and trying to really understand how we can lay the groundwork for maritime applications of advanced nuclear. At the end of the day, NREC really operates squarely in that valley of death between innovation and deployment. Our role is really to de-risk technologies, generate real operational data, and provide clear pathways to authorization. We do this through partnering with developers to turn advanced nuclear concepts into a real operating system and helping move the industry more efficiently towards paths. Right now, we have contracts with about a dozen reactor developers to help with their path to criticality.
All right. Well, Brad, appreciate it. So Rita, you're batting cleanup, and I know you've got a video to share that we're going to share for you. So I'll let you cue that, but over to you.
Great. Thank you. Thanks to ANS for holding this really important webinar to give up kind of progress updates on where all of us are. Radiant is a company that is mass producing microreactors. My name is Rita Baranwal. I'm the Chief Nuclear Officer at Radiant. I've had about 30 years in the nuclear industry. I'm a materials engineer by degrees, but it is because of a van full of interns that I am actually probably here today and have stayed in this industry for so long. I saw a question in the Q&A already about how undergraduates can participate in these projects, and I just want to highlight how important it is for engagement from all levels of education in this industry. The intern story is for another time, but a little bit about Radiant. We are a company that's 160 employees and growing. We did sign the first HALEU allocation contract with the Department of Energy. That fuel is being fabricated into TRISO at our partner Standard Nuclear as we speak. We also signed the first private commercial HALEU contract with Urenco last fall. And why that's important is not only for the fuel, but it sent a true signal to the fuel market that there is a need there. We're all not just talking about it. Some of us are putting our money where our mouth is. And so that was something that I'm very proud that Radiant did. As Brad mentioned, we are the first to go into dome, so that's right behind me. Very colloquially, I talk to Brad all the time. The time to turn those keys over we're counting down the hours. April 1st, we get to start officially moving into dome, and then we get to test our Kairos reactor for a year. So between April 1st and March 31st, we're very, very grateful to INL and DOE for all of the support that we've had over the years to make all of this planning and design a reality. We have three main areas across the country where we have our employees. We have two facilities in El Segundo, California. We are breaking ground at our factory in Tennessee called R50, which is a nod to its heritage at the Manhattan Project sites of K27 and K29, which is where the factory is. 50 for the number of reactors we will produce a year, and R, of course, for Radiant. And then we have our office in Washington, D.C. And so this is where I would like you to cue up the video, if you could, Dan, please.
Hi, everyone. This is Rita Baranwal, Chief Nuclear Officer at Radiant, coming to you from Washington, D.C., and from this dome to this dome. So this is the ramp that KDU will travel up. It'll rotate here and then be moved into dome for our test. I can't wait for that sign to be lit shortly. Join me as we walk into the personnel cab and into the dome. So I'm here for our move-in inspection, where we get to shortly take over the keys to the dome.
Great, thank you for that. So Kairos is a 1 megawatt electric HTGR. It is helium cooled, fueled by, as I mentioned, HALEU that's in TRISO compacts. And we are very much excited to go critical and then to full power. And before I hand the mic back to Craig, I want to give everyone kind of a baseline of when we talk about criticality, what that means. So there's like 5 generally accepted categories of criticality. It's subcritical, approaching critical, dry criticality, hot criticality, and then full power. So Radiant will achieve full power this summer. That is our plan. So going critical certainly is a very important step, but achieving full power several days later is the milestone that we are tracking to. And to give an analogy of what that really means in kind of a layperson's term, subcritical is your car is parked. Approaching critical is that you have released the brake pedal and the car just starts rolling. Zero power critical or dry criticality is that you have tapped the gas pedal and it's moved forward, the car's moved forward a smidge. And then hot criticality is the car drives steadily on a level road. Full power, you're driving on the highway. So with that, we look forward to driving on the highway. I'll hand it back to you, Craig. Thanks.
I love the analogy, Rita. Thank you very much for that. So thank you all. I want to go directly into questions. Jordan, first question to you. So obviously, well, I would say obviously, Artemis 2 is on the launch pad. We may get a launch as soon as tomorrow. It seems to me as though we have some pretty durable policy between administrations, including now with the Trump administration, that nuclear needs to be part of the answer for space exploration. Obviously, the Artemis program, the goal is to land on the pole of the moon. We're going to need, to be able to, we're going to need nuclear if we're going to power any kind of significant base there. Are we at a point now? Because I know in the past we've sort of, had big plans and then we chuck them away and then we make new big plans, but it seems like there's more consistency now. Is that me, or is that how you see things?
No, I mean, it's not just you. I think there's definitely a lot more consistency here than there has been in the past. We believe the market for space nuclear power and propulsion systems will be a lot larger and move a lot faster than I think a lot of people have believed for some time. And I just think there's some mega trends that are driving that. I mean, one is space exploration and sustained habitation in space, and the move to having much more of an industrial economy in space. We'll see orders of magnitude more compute built in space. We're going to have a sustained presence on the moon. There will be increased economic activity between here and cislunar space. But the other thing on the military side that I think is going to drive it is the weaponization of space, right? The physics is pretty clear on this. On a size and weight versus power basis, a nuclear power system has a fixed cost, a mass budget that comes with shielding and how much fuel you need to load to achieve criticality. But once you're above that, call it for sake of argument around 100 kilowatts or so, nuclear actually scales sublinearly compared to solar, right? Whereas solar, there's a linear relationship between power and volume and power and mass, right? So to go to higher power payloads on orbit, I mean, this is fundamentally the way that we're going to do it. As we move beyond 1 AU, right, the further you get out into deep space, there's a 1/r² relationship between solar efficiency, right? So those things have to grow exponentially to be able to produce the same amount of power. It's the only way that we can get into orbit around, outer space bodies, right? So I think it's fundamental. I mean, when I think about, where are we going to be in 10 years and 20 years and 30 years, 40 years, right? If there's human habitation on other bodies, I would not go to any of them if nuclear power weren't there, right? When you think about it from a reliability standpoint. But also, like, if we're mining asteroids, like, we're going to do that with nuclear power, right? It just makes all the sense in the world. I think what I would highlight is, I think on the reactor side of things, I think we're now at a place as a country where we can actually move really, really fast on this technology. Where I think some of our bottlenecks are, it's still, the launch vehicles, the landers, all of the peripherals are still where I think we have to catch up. And it's very rare to think of, an opportunity where the nuclear side of things is actually what's ahead, right? But this is one where I think that's certainly the case.
Yeah, thanks, Jordan. I know you have to take off, but we really appreciate you participating here. So
thank you so much.
You bet. Rita, I want to come back to you. And all right, so I love the analogy. Once you're in dome now, you're not just going to push the pedal to the floor and run for, or will you? Once you've been through that zero power criticality, are you just going to dial it up and let it run? Will you have cycles? Like, how, what is the testing protocol look like?
So part of the plan is to certainly operate at least 150 continuous full power hours without any operator intervention. And why that's important is that that's the generally accepted duration for power ascension tests and new reactor tests. It's not necessarily policy or a requirement, but that's the generally accepted duration. What that does is it thoroughly tests the fuel, it tests the reactor and the reactor materials, and it tests the entire integration of the reactor system. So that's one. The other thing that we're going to do is operate for 60 effective full power days. And that is a similar reason, right, to test out not only all of the components, but then all of the integration and especially of the safety systems. So we have a year to do all of that. If we, I have told my teams historically, there's no penalty for early completion, but if we do complete early, then we can continue to do additional tests until Brad and his team kick us out on March 31st. So there are a lot of tests that we do have planned, but the first and foremost is to achieve full power and sit there, hands off, any of the controls for 150 continuous hours.
Mm-hmm. Mm-hmm. Thanks, Rita. So Yasir, similar question to you. You're building, you're moving, you're getting to July 4th. You hope to achieve criticality. What happens after that? What does the testing protocol look like? How does the next year or so go for you?
Yeah, so Craig, great question. I think it's a similar answer to what Rita was talking about because when you're thinking about a new nuclear reactor program or technology you want to deploy, the most important thing that we have to demonstrate to our customers, to the regulator, and to ourselves is how does it perform in the field, right? And so everyone takes a slightly different approach to how to get those test data. What we have done, we broke those down into multiple iterative steps, right? The first one is the cold criticality test reactor. Why did we go ahead and build this? Because we're not going into an existing facility. We're trying to understand, okay, what is it like to actually go in a full, a barren land and construct something per the nuclear quality assurance program for a full complete building, build the reactor, all the control system, all the electronic systems, and be able to bring power in and test the system basically. But ultimately, what the regulators really care about is, the first reactor is really giving us that physics validation platform, right? So we're going to be measuring a lot of our neutronics parameters, like reactivity wards, Rodworth, how many sensors do we need to actually achieve criticality, and then that is just on the neutronic side of things. We also need similar kind of data on the thermal hydraulics. So we are creating in parallel another test setup, as I was showing in the slide, that is a 60,000 pounds of sodium full scale system that's emulating the primary side and the secondary side, creating all the way from heat generation to steam generation and also powering a small turbine, right? That we're planning to finish off around the July, August timeframe. What that will give us is how do you really take build a sodium cool system and all the various technologies like, we're planning to use printed circuit heat exchangers or, a submersible centrifugal pumps. We're trying to control the chemistry under 5 ppm of oxygen in the sodium. How do we accomplish them on the system level, right? That is something that we're going to be testing out in Aalo 0. And then you basically plug both of those learnings together into the full power reactor, right? So again, these are all iterative stepwise approach. We don't have the liberty to finish one test loop at a time in series. So we're essentially doing a lot of these things in parallel, staggered back to back. So criticality experiment before July 4th, full-scale sodium test around July-ish timeframe, and then we'll finish building the full-scale power reactor, 10 megawatts, at the end of this year, and then turn it on in Q1 of next year. And that will give us the entire gamut of test data that we need. Ultimately, our goal is like, hey, not to reside in the DOE land, but take those data and go and submit that into an NRC license, right? We don't want to send just a packet of safety analyses for our license application. We want to have a good validation data that supports our technology along with it. So all of these test setups that I talked about will essentially generate those data. Again, we've done a lot of work in the past in sodium cool technology, but that unique combination of sodium with graphite moderator and UO2 fuel with Zirclad with 8% fuel. There's some unique domain data that is unique to us that we'll have to generate that does not exist today.
Got it. All right. Nader, coming to you now. Kairos has chosen to go down the straight NRC route, but you've still found a way to iterate in much the same way as the other companies have. What are some of the unique challenges and opportunities of working within the NRC system as opposed to the DOE system?
Sure. Craig, our experience with US NRC has been a successful story. And the key aspect of that strategy has been early engagement with the regulator. So that was basically baked into our strategy from very early on. And obviously breaking it down to a test reactor, small test reactor, which has a very small source there, very small fluence, radionuclides, so on and so forth. It obviously makes things a little bit more, it gives you more margin. It doesn't make it easier for tools and methods and testing that should come together to construct the safety case, But what it does is it gives you the margin to be able to go through the review process a little bit. You can spend that margin to go faster in the licensing space. That's one aspect of it. The other aspect, as I pointed out, we started engaging with US NRC very early on. We have 14 topical reports with US NRC approved. Each one of them will take a significant amount of resources, but on the back end, it saves quite a bit of time when we try to deliver reactor at scale. I also want to point out, iteration is also on the licensing space has been really helpful for us. I may get the numbers wrong, but the construction permit for Hermes test reactor, which is its own, was the first of a kind, happened. I may have it in my notes. I think it took about 21 months to be issued. And Hermes 2 reactor, the construction permit, it dropped down to 14 months. So we were able to show that the iteration also works in the US NRC space, because the safety case and basically the construct of that, those arguments are very similar between the 2 reactor. So that has also been very helpful. But again, I'm going to go back to the first slide that I showed. Kairos is basically taking the posture of delivering reactors at scale, and working with US NRC from early on allows us to get to that milestone, very much aligned with our hardware delivery of Hermes 1, Hermes 2, and the fleet that comes after that.
Yeah, thanks, Nader. So I have so many questions. I could do this for another 2 hours, and I'm sorry we're not going to get to a lot of our audience questions. I want to ask one question of our folks that kind of represent the lab or the government side of the equation here. It's kind of the same. It's really the same question, which is, okay, we're seeing criticalities now. We're seeing, a walk down the TRL levels on all of these things to the point where we're going to get to commercial operations soon. So is this a point at which the national laboratories say, well, job done, I'm good, and then it's the private market that takes over? Or I imagine the answer is there has to be some kind of ongoing role or unique role or assistance that laboratories can provide as the nuclear innovation process continues. So Nick, I'll go to you first, and then Brad, speak a little bit to that.
Yeah, I think the labs do have a unique role in being a bridge from early technology and developing that so that companies can actually use it and deploy it later. So my background is actually in nuclear data, and my advisor, he would always say that, this is 10 years ago, the only people who are funding nuclear data work was the Nuclear Criticality Safety Program and then the Navy, because those are the only people who are actually building things, right? And now we're seeing all these companies doing experiments with us because, they're trying to build something, they're trying to get that data they need to actually deploy. So I think there's, one good example of that is TerraPower. We've done a lot of work with TerraPower, both at NSERC, but also at the accelerator at Los Alamos here, to get better data on chlorine for their molten chloride reactor, because there were some pretty big uncertainties in chlorine, and we've been able to improve that chlorine nuclear data for everybody in the entire community because of that work. So there's definitely a big role to play, and there's always going to be work to do.
Yeah. Thanks, Nick. Brad, I think you get the last word here.
Oh, nice. So just first and foremost, Enric is here to provide the capability to make life easier for these developers, as easy as they can. Most of these projects are funded, the actual testing is funded by the developer themselves. For example, Radiant's in full freight to come into the dome to test. So our role is really to make sure that we have what we need in terms of infrastructure, but also in terms of expertise. So we have at Idaho National Lab, we have a really robust team that knows how to do the nuke safety documents for DOE authorization. And so we bring that to the table as well. We've been through this with so many of these companies. We recently had a company come to us last fall. We've already got their PDSA submitted. And so that's almost like a record time for getting that through. But this is kind of how we're getting to the point where we work hand in hand with DOE. We have an integrated team. So we integrate the team with the developer, with the INL and the INRIC team, and with the DOE ID team. And so we work all hand in hand along the whole way to really get these things to criticality. And I think that's what works. So I have people out in Escondido with Radiant right now. We have people with Radiant coming up to Idaho and spending time. DOE ID is with us the entire way. So this integrated team is really how we're making these things go so fast. And I think that's here for at least the next 10 years or so. We're going to have this kind of thing going.
Yeah.
There's a lot of reactor developers waiting in the wings to use Dome, to use the launch pad. And there's a lot in addition to the reactor developers, we have fuels and other folks that want to use these things as well. So I see us having a role to play for at least the next 10 years.
Yeah. Well, thank you, Brad. And I think, again, the sort of the readout of this is things are moving faster, and we're moving down the development chain in a way that we couldn't even think possible maybe 5 years ago. And so, but that doesn't end with the first commercialized reactors. There's an innovation process that will continue to occur, that will happen in companies. It'll happen and as a result of collaboration and the resources of the National Laboratory System. And one expects that we will see significant numbers of megawatts to gigawatts of power being added to the grid here in the next few years. So with that, we're a couple minutes over, but I wanted to thank all of our participants. It's a really fascinating conversation. I think the nuclear community is cheering you on in your progress. And we look forward to continuing the conversation and hopefully seeing where you are in maybe 6 months or so, and if it's proved out the way we thought it would. But until then, thank you. I want to thank the audience, and I hope we've made your week a little bit brighter. Thank you all.
Thanks, everyone.
Thanks a lot.